Supplemental math videos from Circle Christian School.
This is your function study guide for advanced math with exponents, complex numbers, complete the square, and the quadratic formula. Why do we factor these polynomial functions all the way down to the factors? Well, of course, it's to find the value of x. We call those the roots because actually when you complete the square, you're doing square rooting. That's one of the reasons why it gets called the roots, the zeros, the x-intercepts. And sometimes we just need to take exponential variables and use our complex numbers for different things. Yeah, enough said. First, we're going to work with exponents. Just a little reminder that you are working with a base and a power. And that power, since fractions are real numbers, can actually be a fraction. Now we're going to check out our exponent rules. The number one exponent rule, the product rule, says same base times same base, we're going to add the powers. The quotient rule says same base divided by same base, we subtract the powers. The negatives, remember, we just slide them over the fraction bar and make them positive. And then the power over power is you're distributing that power to every base that's inside there, whether it's a number or a variable. And it's about multiplication. So to use these exponent rules, since an exponent or the inverse of an exponent is a radical, sometimes it's to our advantage to change a radical into an exponential equation. The key here is to remember that it's always the inside power over the outside index. That is, if we have an index of n root over the base x to a power a, then we would have x a over n. There's our fraction. So the square root of 4 equals 4, 1 over 2. That is, 4 has a power of 1, and a square root has an index of 2. Cube root of 8 is the same as 8 to the power of 1 over 3, because the inside power is 1, and the outside index is 3, so 1 over 3. Something that's a little bit bigger here, let's take the cube root of xy squared. It would equal x to the 1/3, because x has a power of 1, and y to the 2/3, because y has a power of 2. Moving down to a real operation here, the reason why we change these radicals into being exponential is that generally we can't multiply different types of radicals. Here we have a square root and a cube root. So in theory, we can't multiply them together in this form. However, if we change them to be exponential, the first one being 6 to the 1/2 times 6 to the 2/3, and remember it's inside power over outside index. It's where the 1/2 and the 2/3 comes from. We can now go same base times same base, we add the powers. So here I changed the fractions to have a common denominator of 6, 3 over 6 plus 4 over 6. And our final result would be 6 to the power of 7 over 6. Likewise, when we take a same base and divide it by a same base as a radical, if the index isn't the same, we can't do it unless we change it to be that exponential. That is, we're going to give it an exponent. Giving it an exponent now takes us back to those exponential rules. And here The square root of x over the cube root of x is the same as x to the power 1/2 divided by, oh, I'm sorry, that's a 5, that's not a 3, divided by x 1 over 5. And now it's top exponent minus bottom exponent. So x 5 over 10 minus 2 over 10 equals x 3 over 10. Just because it's in one form doesn't mean we can't complete the problem as long as we change it into another form. Complex number properties and operations. What happens when we end up with a negative number under a radical? Well, it stumped great mathematicians for many years. But when they eventually found a way to give it a value, in this case they gave the square root of -1 the value of I, they were then able to take all these negative radicals or negative square roots and now use the same real number properties and operations that we apply to numbers with imaginary numbers. Changing a square root, in this case square root -1, we call it I. Square root -4, the square root of 4 is 2, and that negative says I. Square root -8, the square root of 8 is 2 square root 2, simplified, and the negative says I. The two big ones that we use with complex numbers is the square root -1, or I squared, which is -1. Because a radical times a radical always equals the number underneath the radical. We can use power remainders of radicals so that we can simplify rather large powered imaginary numbers. The thing that you have to remember is that I to the first power has a remainder of 1, I to the second power a remainder of 2, I to the third power a remainder of 3, and I to the fourth power, which equals 1, has a remainder of 0. So I to the 15th power is 15 divided by 4, or 3 with a remainder of 3. Therefore, it's -I. I to the 24th power is 24 divided by 4. Imagine there's a 4 there. I forgot to put it in. It's imaginary numbers. We can get away with it. Is 6 with a remainder of 0, so I to the 24th power equals 1. We can add and subtract and multiply just like we do with real numbers. We just need to distribute, combine any type of like terms. So 2 times the 8 gives us a 16i, real number to real number, I to I. 2i times the positive 4 gives us a positive 8, I times I, -1. All right, -6 distributed, -6 times the 2 gives us a -12. -6 times the -3 gives us a positive 18 and an I. And so now we're just going to combine our like terms. And we get, and generally you put the real number first and the imaginary second. So -8, -12 is a -20. And 16 plus 18 is 34, positive 34. And an I. Okay, now the only thing that's a little wacky doodle here is the fact when we have to divide that you can't have an imaginary number or an imaginary equation down in the denominator because it's just not real. You can't equally cut up a pizza into unreal slices. So to make it real, what we're going to do and what we found out is that we can do a conjugate, or that is the difference of two squares. And whatever you do down below, you have to do up above. Sorry, that should be an I. Okay, down below, difference of two squares. 6 times 6. First one squared, 36. Second one squared, I squared, which is your -1. And the difference of two squares always has a minus sign. So we get 37. Okay, up above, we're going to do that distributing thing. 3 times 6 is 18. 3 times the +1. Today when I was watching people try to FOIL some of these things, I noticed you weren't using things like arrows. Therefore, you were getting lost. You were trying to do brain work. Get over it. Make arrows. 3 times an I is a +3I. In fact, I'm going to move to a different color just so I can see it a little bit better. 4 times 6 is a +24 and an I. And 4I times the I is a +4 and a -1. You kind of squishy there, so I'm going to combine my like terms. And my like terms here, I'm going to take my real stuff, which is my 18, and my -4, so I get a 14, 3I, 24I, +27I. And the way you would see this is real stuff up front, and imaginary stuff at the back. And since they're fractions, you simplify appropriately. So it just follows real number operations. We graph complex numbers just like we graph our real numbers. The only difference here is that our x-axis is the real part of an equation, and the y-axis is the imaginary part of the equation. And what I'm going to do here is the real part is known as a, while the imaginary coefficient is known as a b. That's what we're going to end up graphing. So if we have 2i and there's no a, that means it's a pure imaginary number, so there isn't anything real. So we start at 0 for our x-axis here and walk up 2. And generally when you're doing imaginary things, you'll put your coordinates so that you know what the equation was, kind of thing. Number 2, we have 3 minus I. So the real number is 3, so we walk over 3. The imaginary part is -1, so we're going to walk down 1. And so that gives us a 3 -1 I. Okay, kind of hard to see that negative because of the blue. Should have used a different color. Okay, 5 plus 3i. And walk over to 5, go up to 3. I think you get the idea here. It's not really all that complicated. That's the neat thing about complex numbers, is they just went into another realm here, what to do with negative square roots, and found a solution to them by using real number properties. And then 2, -3, 1, 2, -3. All right, now the z-value, or what works into what we call the Mandelbrot set, is the distance that this is from origin, or 0, 0, and it's the square root of the a squared plus the b squared. So generally, basically what we're talking about here gives us a bit of a right triangle. Let's see if you can see my little green going on here. Here's that right triangle. And this is the a, and this is the b values. So this would equal the square root of 5 squared plus 3 squared. We're just talking about the coefficients here. The I just gives you basically your y or your vertical axis. And it would equal the square root of 25 plus the 9, or the square root of 34. Would equal that part of the Mandelbrot set. All right, we're going to complete the square. The second time we're going to do it because I hit the wrong button. So much fun. All right, to complete the square, we have x squared minus 2x plus 4. And to complete the square, we have to jump the 4 over to the other side here. So we take the middle number, divide it by 2. That's going to give us the amount of tiles that we add. And the amount of tiles that we're going to add is going to be a -1. And if we add -1 to one side, we have to add -1 to the other side. Now the whole reason why we do this, so we can get this perfect binomial squared, which is just the number inside here. So it's going to be x minus 1 and -4. And remember, any binomial squared, so -1 times -1 gives us 1. -4 plus 1 is our -3. Now I'm going to rewrite this just so you can see it a little bit cleaner when I do my work. Okay, the whole reason why we do this is so we can square root both sides. Complete the square so we can square root. And anytime we square root, the value is always going to be a plus minus radical. And so we have the x minus the 1. And in case you didn't really see it earlier, a binomial squared is x minus 1 and x minus 1. It's under a radical. It's like having a 5 times a 5, and the thing that comes out would just be the one thing. Remember, it takes 2 for 1 to come out. Equals, and I'm going to leave a space here because I'm going to do some jumping, plus minus. We're going to simplify the radical. In this case, it's an imaginary number, a complex number. So square root square root 3i. So we're going to take this -1 and jump it to get the x by itself, and we get 1. And so our final answer is x equals 1 plus or minus square root 3i. The reason why we complete the square is so we can square root. Now, if you were to graph this equation here, the way it would look on a coordinate plane, sorry that that's so crooked. Sometimes the tablet doesn't work as well as it should. But you would see you'd have a parabola that does not cross your x-axis here, so therefore it doesn't have any roots, zeros, or x's along the x-axis. It's kind of up in the air or down below the x-axis. It's complex. You can graph it. It's there, but it doesn't really have any roots but yet it does. Now, the default method for any quadratic equation to go find x is to just use the quadratic formula. It bypasses having to do any double bubble factor by grouping type of thing or complete the square. Most of the time, the most effective way is just to use the formula negative b plus or minus square root of b squared minus 4ac all over 2a all over 2a. The big thing is to identify what your a, b, and c is and to make a template. All you guys that end up spending way too much time trying to go solve these are not using a template and you haven't identified, put down on paper what A, B, and C is, and you want to make your work twice as hard. Okay, so there's a 1 here. So there's your A. There's a B here. It's -8. But quadratic equation has everything equaling 0. So that 11 has to go and jump. So C equals the -11. And I'm going to actually write it right next to everything because then I have a reference point. You can be as smart and as brilliant as a rocket scientist, but if you don't have checkpoints, you don't have templates for your formulas, you're going to miss a negative and you're going to take too much time. So now I'm going to fill everybody in. I'm going to fill in all my A's, fill in all my B's, and then my C's. Parentheses keep the integers happy. Today when we worked, the thing I saw was that people did not watch their integers, and it's because they didn't use parentheses, they didn't move things over, they didn't identify. They did stuff in their head. Okay, going to simplify the real parts up front here, and it's possible we end up with real stuff in the back too. It all depends on the discriminant. I'll talk about that in a minute. -8 is an 8 over 2, and simplifying that, went too far because that's going to work into my discriminant. Simplifying that is going to give us a 4. And so I set it up so that I have a 4 plus or minus what's happening with all this radical stuff, which can give me a real number, it can give me an irrational number, or it can give me a complex number. Just depends. So now we're going to do simplifying. The -8 squared. Anything squared is always positive. So we have 64. Signs first, math second. I have a negative, so it's going to be a positive. 4 times 11, 44. Which gives us 108 square root of over 2. We have to simplify the 108. 9 and 12. 3 and 3. 3 and 4. Okay, so a 3's coming out. 2's coming out. 3 stays inside. So we end up with 6 square root 6 over 2. Simplify. We get 3 square root 6. Here's your irrational answer. Okay, this is your lucky day. I'm going to white out that 6 because you were probably jumping up and down anyway going, Mrs. Washington, that's a 3. And it is. So I need to white out those 6s. Make it a 3. Sorry, guys. However, if you saw that mistake and yelling and screaming about it, make sure that you put in your video notes a plus 50 stars. Boop, boop, boop. Can't read my own writing. Okay, that little discriminant guy. The little discriminant guy is the part of the formula that's under the radical, the b squared minus the 4ac. And sometimes you can figure out how many answers you have by just looking at this part here. If what happens underneath here gives you a 0, you have one real answer. If what happens under here gives you a perfect square root, or it gives you a nice radical, you have 2 real answers, or 2 radical, or what we call irrational answers. And if you end up with a negative underneath the radical here, you have 2 imaginary answers, 2 complex numbers. Okay, so you end up with 2. And that's just kind of a nice little double check that helps you figure out, did I get the right answer or did I not get the right answer? So what do you need for this test? Make sure you got your spiral notes and your 3-ring binder. Make sure you have a calculator. You're not going to be able to use mine. You're going to need the notes from this video. And you're going to have a Reinhold tough attitude. RHINO stands for Real Hard Input Influences Output. You're going to need to know that. Okay, guys, breathe. It's okay. If you did everything that you were supposed to do, you're going to be totally prepared.